Hello everyone, welcome to Chapter 9 of Chem 112 with the TRO book, and this is Dr. Rhonda Kofelt. And the first part of this, we're kind of reverting back to Chapter 9 for thermochemistry, and then we'll cover Chapter 18, which is more of the thermodynamics. So in this chapter, we're going to look at enthalpy changes primarily. This is the second half of Chapter 9, and so we're just talking about enthalpy. So in the first part of this, we're going to look and see kind of what we mean by is it endothermic or exothermic, and what would the sign of the delta H, just kind of a review. And then the second part of this, we're going to do stoichiometry calculations and see how delta H is involved in that. So the enthalpy of a system, and that's H, is the sum of all the internal energy of the system, and it can also be the product of pressure and volume. So the one type of work you can do is called pressure volume work, and that's if you have gases. And so that's why this is part of this equation. And so H is a state function, so enthalpy is equal to the internal energy plus any work done by pressure volume. Now if you don't have gases, you're not going to have that. The change in enthalpy of a reaction is how much heat you evolve in the reaction if you maintain constant pressure, okay? Constant pressure and volume. And so if you're constant pressure and volume, then you can disregard those because they're not going to change. And so then you can look at the change in enthalpy of the reaction. It's going to be equal to the Q of the reaction, and you remember Q is the heat. Okay, that's when we can measure that easily. All right, so usually delta H and delta E are similar unless you have lots of gas involved, and obviously that's going to then bring your pressure volume back into play. So as long as we're not using a ton of gases in the system or just primarily gases, then we won't see much difference, and so we can use the delta H or the Q to estimate what that change in internal energy is. When the delta H is negative, heat is being released by the system into the surroundings. That is an exothermic reaction. So heat exits, and you have a negative delta H. And if you put your hand on that, your beaker will be hot because you are generating heat, okay? So the temperature of the surroundings increases from the energy that's being released by the system. When delta H is positive, okay, a positive delta H, that means that heat is being absorbed, and that is an endothermic, okay? So we think of the words that go together in these are released heat, okay, exit system, negative delta H. Those are all exothermic. In the delta H positive, it's absorbed energy, okay, it's endothermic, all right, and so it will feel cold if you touch it, all right, and so when we can do face-to-face labs, we do this a lot of times so that you can actually feel the difference in the temperatures between the two reactions. So from a particulate standpoint, the temperature of the surrounding rises because you're releasing thermal energy. Okay, so the energy that you were storing in those chemical bonds is being released into the surroundings and causes a rise in temperature. The extra thermal energy comes from that potential energy, okay, and so when we're breaking those bonds, the potential energy that was being held in the reactants is now becoming part of the product, and so you're producing heat. All right, so also another way of looking at it is that the products are going to have less potential energy than the reactants, and the difference between those two is released as heat. In the endothermic reaction, the opposite happens. The temperature of the surrounding drops because you're absorbing thermal energy. The existing bonds are broken and new bonds are made. The products though are going to have more potential energy than the reactants. All right, and so in order to get enough energy for this one to occur, you have to actually pull some energy from your surroundings. So this is just kind of a fun little thing to get your brain started thinking about this, and because you kind of have to think outside the box just a little bit. And so in these everyday processes, which would be endothermic versus exothermic, and then what is the sign for the delta H? So when sweat evaporates from the skin, so sweat is evaporating from the skin, okay, not when you're sweating, but when you're evaporating. That's actually an endothermic process, all right, which is a positive delta H because you are absorbing energy from the outside in order to cool that down. So your system, which is your skin, cools down. Water freezes. In order to freeze something, what do you have to do? You have to lose heat. So if you're losing heat, that's going to be exothermic. Wood burning in a fire. Okay, this one's easy. This one you're obviously doing what? Releasing heat. So that one is a negative delta H. All right, so it's just kind of a way of thinking about this because part of the process, if you recall from 111 when we were doing some of this, was figuring out what the system is. What's the system versus what is the surroundings? So the enthalpy change is an extensive property. Okay, and if you remember, that means that it does depend on amounts that you have of each thing. So we calculate the enthalpy of change typically for ever how many moles of reactants you have. And so when you have propane and you add oxygen to it, you're producing 3 CO2 molecules and 4 waters. We know that's combustion, right? It's the classic combustion. Add oxygen to it and produce CO2 and water. The delta H for this reaction is exothermic. When you're burning this, okay, you're producing a negative 2044 kilojoules. And that's important because you need to figure out a lot of times how many kilojoules you're getting out of that reaction so that you can heat a room or whatever. All right, so in this particular case, you've got 1 mole of propane. So for 1 mole of propane, you're producing a negative 2044 kilojoules. You're also, for every 5 moles of oxygen, you're producing that. But we typically think of it in terms of whatever the fuel is, okay, because that's really, oxygen probably wouldn't just sit there if it didn't have something to act on. So you look at it from the standpoint of the propane, and you have 1 mole of propane, so that's a negative 2044 kilojoules per mole of propane. So that's just how we look at it, okay, in molar ratios, because it's an extensive property. So that allows us to do stoichiometry with this. Yes, you're not going to escape from stoichiometry ever. And so this is the reaction I was just talking about. So if I have 13.2 kilograms of C3H8, oh, no O. So I have 13.2 kilograms of this propane, and it wants to know what the heat associated with it is. So I know that for every 1 mole of propane, I get this amount of heat. So I'm going to have to figure out how many moles I have. So this is your standard dimensional analysis. Convert it to grams. Then convert it to moles. Right? Then you're going to multiply it by the negative 2044 kilojoules per mole of C3H8. And then you're going to be able to punch that in your calculator, and you're going to get a negative 6.12 times 10 to the 5th kilojoules is going to be it's going to be given off, right? Because this is exothermic, because you're releasing that much energy. All right, so that's a really simple calculation. We've done these over and over again, so you shouldn't have any trouble with these. As always, I give you a couple to practice on to make sure that you've got it. So feel free to stop here and do that. Notice something you may not have seen before. You can have fractions of oxygen when you're doing some of these reactions. That was a big no-no for us. We wanted to just have those numbers. The reason they do that is because that's kind of how they get one mole of something a lot of times, which makes the calculation easier. And also because we're really not looking at oxygen when we're doing these calculations, we're looking at the fuel. Okay, so that's why you do that, unless it's a limiting reactant, which typically you've got all the oxygen you need. Okay, so that's why you can do 13/2 oxygens and you don't care. Okay, and that's it for the first part.